Welcome to this explainer. We're diving straight into the PSRU Prayagraj syllabus today to break down exactly how you can conquer its intense 5-paper M.Sc math requirements in just a single semester. If you've been searching for an effective M.Sc mathematics study schedule that actually turns a massive mountain of advanced theorems into a totally manageable victory, well, you are in the exact right place. So let's just address the elephant in the room. Facing 25 units of highly advanced mathematics without a rock-solid chronological strategy, yeah, that's basically a recipe for absolute burnout. You can't just open a textbook and read from page 1 to the end when you're juggling this many completely different branches of math all at once. To fix that, we've broken this down into 4 phases: core foundations, applied tools, complex numericals, and a final polish. Just think about the sheer scope of what we're up against across these 5 heavily distinct papers. We aren't just learning one flavor of math here. We are going to be bouncing frantically between algebra, analysis, research methodology, PDEs, and differential geometry. It is a lot to process. To survive this, it absolutely requires anchoring our study to a master timeline. By tackling specific papers exactly when they yield the highest strategic advantage, we can compartmentalize the semester. This way, you're only ever focused on the right type of thinking at the exact right time. Section 1, Core Foundations, our August to September strategy. Your first mission in August and September is locking down the core theory from papers 1 and 2. In Algebra 1, you're going to immediately hit advanced group theory, which means you absolutely have to master structural proofs. Silos theorems, for instance, are going to act as your primary key for unlocking those numerical problems that ask you to find all non-isomorphic groups of order PQ or P squared Q. And that brings us to a huge focus for Algebra Unit 3. You have to strictly differentiate between solvable and nilpotent groups using counterexamples. It turns out it is nowhere near enough to simply memorize these definitions. You literally have to be able to prove their structural differences on the fly. Over in analysis, we're applying that exact same comparative rigor, but to sequences and series of functions. A foundational skill you need to secure early on is determining uniform convergence regions using the Weierstrass M-test. You've got to know exactly how to distinguish that from mere pointwise convergence. So, by the end of September, the syllabus demands that you've conquered polynomial ring factorization chains. Think of them almost like mathematical nesting dolls. You're proving how a Euclidean domain implies a principal ideal domain, which then implies a unique factorization domain. You also need to have topological proofs and multivariable derivatives totally locked in before we pivot our strategy. Section 2, Applied Tools, the October strategy. Moving into October, we are temporarily putting down the pure theory to master applied mathematical tools. For paper 3, which is research methodology, you're going to learn to execute 4 exact steps: identify, formulate, solve, and conclude. We're shifting gears from solving established proofs to learning how to frame brand new mathematical problems from scratch. The crucial takeaway for October is getting your hands dirty with digital tools. You have to get comfortable with LaTeX syntax for formatting complex equations, you need to know how to navigate databases like MathSciNet, and you have to grasp exactly how the IEEE and AMS structure their publications. This is also the month we dive headfirst into paper 4. The heavy lifting here? Converting general second-order PDEs into hyperbolic, parabolic, or elliptic canonical forms. Plus, you'll be using the separation of variables method to completely conquer Laplace, heat, and wave equations. Now, for the nonlinear portion of this paper, you'll specifically need to master Monge's method. It's the exact tool you need in your arsenal to solve second-order PDEs, formatted specifically as capital R, lowercase r, plus capital S, lowercase s, plus capital T, lowercase t, equals V. Section 3, Complex Numericals, the November strategy. Welcome to November. This is, without a doubt, the most computationally heavy month of the entire semester. Paper 5, Differential Geometry, takes center stage right here. You'll be computing curvature and torsion for space curves, kind of like calculating the physics of a roller coaster, and you'll be using the Frenet-Surret formulas as your main engine. We're also evaluating minimal surface conditions and deriving differential equations for geodesics. Here's the thing about proving Gaussian curvature and computing Christoffel symbols. It's not something you can just conceptually understand. Your hands literally need the muscle memory of doing these repetitive, complex calculations. Right alongside that geometry, you'll need to rigorously practice converting between differential and integral equations. A major focus is taking initial and boundary value problems and morphing them into Volterra and Fredholm integral equations, all while finding exact solutions for separable kernel problems. You'll round out those November practice sessions by solving contour integral problems and applying Rouché's theorem to count the zeros of complex polynomials. This brilliantly brings some of that Phase 1 analysis theory back into play, but this time it's purely through the lens of complex numerical application. Section 4. Final Polish, the December Strategy. So December arrives and our strategy shifts one last time. With exactly 1 month left, there is absolutely zero room for learning new concepts. Your schedule must be exclusively dedicated to synthesizing the 25 units you've already covered. If you haven't learned it by December 1st, you really just have to let it go. During this final stretch, simulating actual exam conditions is critical. You need to ensure your proofs for the isomorphism theorems and those grueling contour integration calculations actually hold up under pressure. This is how you prove that your effective M.Sc mathematics study schedule translates into real-time performance when the clock is ticking. By strictly adhering to this phase-by-phase chronological roadmap, we can literally transform an impossible-looking syllabus into a highly manageable victory. The schedule is set. But here is the real question for you. Once you clear away the panic of deadlines and exams, what deeper underlying mathematical truths will you uncover along the way?